Okay, let's jump right into this explainer and set the stage for what is honestly one of the greatest intellectual detective stories in the entire history of mathematics. We're going to explore how humanity took an impossible, literally infinite problem and rapidly shrank it down to size right before our very eyes. So, I want to start off by asking you a question. It's a question that has completely baffled humans for well over 2,000 years. Think about the endless number line. As we count higher and higher all the way out toward infinity, do prime numbers eventually just end up totally alone? It's a super simple question to ask, right? But as you're going to see, finding a rigorous mathematical proof to actually answer it has proven to be incredibly tricky. Now, just to make sure we're all on the same page, let's quickly touch on the basics. Prime numbers are essentially the indivisible atoms of math. We're talking about numbers that can only be divided by themselves and 1, so your 2s, 3s, 5s, 7s, and so on. Every other whole number is basically built by multiplying these prime atoms together. But the real star of the show today is something called twin primes. These are pairs of prime numbers that sit as close together as they mathematically possibly can, separated by a gap of exactly 2. Think of pairs like 3 and 5, 5 and 7, or 11 and 13. You can kind of think of the number line like this vast, dark universe. And the further out you travel into this universe, the rarer primes become. The mathematical gaps between them widen exponentially, growing roughly at the rate of the natural logarithm. And because they get so unbelievably rare, you can't just use a supercomputer to physically check all the numbers out to infinity. There's literally not enough computing power in the universe. Instead, you absolutely need bulletproof mathematical logic to prove that these twin primes never stop popping up. Well, since we obviously can't physically check every number out to infinity, mathematicians historically turned to a brilliantly simple 2,000-year-old tool. It's called the sieve of Aristophanes, and it works exactly like a physical sieve. Imagine a massive grid of numbers. First, you cross out all the multiples of 2. Then you cross out the multiples of 3. Then 5, and you just keep going. Whatever numbers manage to slip through the holes of this mathematical filter and stay on your page, boom, those are your primes. But here's where it gets complicated. Counting what actually remains at the end requires a technique called the inclusion-exclusion principle. And here's why that matters. If you cross out multiples of 2, and then you cross out multiples of 3, a number like 6 actually gets crossed out twice, right? So to get a perfectly accurate count, you have to mathematically add it back in. And this constant back-and-forth dance of subtracting and adding creates this massive snowball effect of tiny little rounding errors. By the time you try to push this sieve all the way out toward infinity to find twin primes, those accumulating errors pile up and form this impenetrable, massive mathematical wall. Okay, so how do we get around that wall? Well, modern mathematicians developed what are known as analytic sieves. Instead of treating the sieve like a filter, they treat it more like a sliding stencil. Imagine taking a stencil with very specifically cut holes, and you slide it along an infinitely long piece of paper. If you can mathematically prove that infinitely often this stencil happens to catch at least 2 primes simultaneously inside its holes, then you've done it. You've successfully proven a bounded gap between primes. Now, for decades, researchers were just completely stuck. They couldn't push their stencils past this highly technical roadblock known in the math world as the one-half barrier. But then, in 2013, mathematician Yitang Zhang totally shocked the world. Out of nowhere, he found a way to bypass this barrier, proving for the very first time in history that there are infinitely many pairs of primes separated by a bounded gap. And that gap? It was 70 million. Sure, 70 million is a whole lot bigger than our twin prime target of just 2, but it was a completely monumental leap. It was the absolute first time anyone had proven the gap was a finite number instead of just infinity. And honestly, what happens next beautifully illustrates the snowball effect of mathematical progress. Because literally just months later, in late 2013, a postdoctoral researcher named James Maynard came along and dropped that brand new record of 70 million all the way down to a staggering 600. I mean, it was just an absolute explosion of progress. It's super fascinating to compare how they pulled this off. Zhang achieved his breakthrough by basically refining the mathematical inputs. He proved these incredibly strong results about primes and fed them into the existing sieve method to bust right through that rigid one-half barrier. Maynard, on the other hand, he completely reinvented the sieve itself. He completely shattered the rigid symmetry of the older methods and built a multidimensional tool. This meant he could evaluate variables totally independently, which required much weaker inputs to get a dramatically smaller prime gap. This massive wave of momentum sparked an unprecedented online collaboration known as the Polymath project, spearheaded by legendary mathematicians like Terence Tao. The entire global mathematical community basically rallied together. They took Zhang's highly refined inputs and smashed them together with Maynard's newly invented multidimensional sieve. And working collaboratively over the internet, they just continuously optimized and tweaked this massive mathematical machinery. And through this totally unprecedented shared effort, the unconditional record gap was drastically reduced to exactly 246. Think about what that means. We now know with absolute 100% mathematical certainty that as you count out to infinity, you will infinitely often find pairs of prime numbers that are separated by no more than 246. When you actually put this timeline into perspective, it's just staggering. Before 2013, the proven gap was literal infinity. In early 2013, Zhang wrinkled it down to 70 million. By late 2013, Maynard crushed it to 600. And by 2014, the Polymath project locked it in at 246. In barely over a year, humanity closed the gap from infinity all the way down to 246. It honestly makes abstract number theory feel like this incredibly physical, rapidly shrinking distance that we're all just sprinting across. Okay, but you might be wondering, why are we currently paused at 246? Well, it's because of a fundamental limit built into the multidimensional sieve itself. It's called the parity obstacle, basically a mathematical roadblock where the tool just fundamentally stops working. Even if we magically assume that some major unproven mathematical conjectures are completely true, this specific multidimensional sieve tops out at a theoretical limit of 6. Which means we literally cannot reach that final twin prime target gap of 2 without someone inventing a completely brand new mathematical tool. So, I'm going to leave you with this incredibly optimistic thought from James Maynard himself. He pointed out that, sure, we might be paused at 246 for the moment, and it absolutely requires a massive new concept to cross that final finish line. But we are very likely only one big idea away. Think about it. We've literally watched the gap shrink from infinity to a mere 246 in our own lifetimes. The next great breakthrough is out there right now, just waiting to be discovered. And who knows, maybe someone watching this very explainer will be the one to have that final big idea.